Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are going to talk about the paper data structures. Now, in this module we are going to talk about tree ADT, the same as we spoke in the last module, but here we are going to concentrate on binary trees, which is the most frequently used tree structure in computing. So, let us these are the people responsible for the creation of this particular module. And now let us look at what are the learning objectives of this particular module. We are going to compare general trees and binary trees. In the last module we spoke about general trees. So, we are going to compare the two. Then we are going to discuss binary trees in detail with some examples, and then we are going to describe some operations on binary trees, and then discuss the various representations of binary trees and the different tree traversals, and we are going to explain the various tree traversals. So, these are some of the issues we will be talking about in this particular module, and the keywords are trees, binary trees and traversals. Now, let us first compare general trees and binary trees. Now, a general tree is a set of one or more nodes such that T is a particular is partitioned into disjoint subsets. We are not saying how many subsets. So, you have a node R, the root, and the sets that are general trees called subtrees of R. This is the definition we gave for a general tree before. A binary tree is a set of T, which is again of nodes, that is partition. T can be empty, or T is partitioned into three disjoint subsets. One is the root, specifically designated node called the root R, and two possibly empty sets or can be empty, that are binary trees, which are called the left and right subtree of R. So, a binary tree will have a root and a left subtree and right subtree. It is not necessary that every subtree should be having nodes, but it is defined that way. Now, binary tree is an ordered tree with the following properties. Now, in general tree we basically called it as left most child, but actually there is no order to the children of a general tree. The order is not specified because we do not know how many children it has. Though when we spoke in the last module we did talk about the leftmost child, we also spoke about first child, but there is no designated ordered concept to the general tree. So, a binary tree is an ordered tree with the following properties. Every node has at most 2 children. So, it can have 0 child, 1 child, but the maximum number of children it can have is 2. Each child node is labeled as either a left child or a right child. There are only 2 possible child that can a parent can have, a left child, a right child, only left child, only right child, or no child. A left child precedes a right child in the ordering of children of a node. This is what is different in a binary tree. The order is specific. So, a general a binary tree with the order of the children different is a different binary tree. So, a left child precedes a right child in the ordering of the children of a node, and children form an ordered pair. Only 2 children, they form an ordered pair. So, maximum number of nodes in a binary tree can also be specified because everything is specified, maximum number of nodes. So, a root node will have no parent, all the leaves node will have no children, all other nodes can have 1 child or 2 child. So, here assuming maximum number, the maximum number of node of depth I of a binary tree is 2 to the power of I. Depth I is the number of levels it has, where I is greater than or equal to 0. The maximum number of nodes of a tree of height k is 2 k plus 1 minus 1, where k is greater than or equal to 0. So, I will go into detail about this as we go along. So, let us take a binary tree ADT. As you remember, this course, complete course or paper on data structures is looking at the abstract data type viewpoint. In general trees, we did not go too much into the abstract data type because we were introducing the concept of trees there, and most of the implementations and data structures are to do with binary trees. So, binary tree T has a root node R, and it has a left binary tree TL and a right binary tree TR. Now, this is a subtree, okay, we are assuming it is a subtree. So, nodes with no successors are called children, and the node or no descendants. The nodes of the left and right subsets of subtrees of a node I are called the children of I as before. A node I is their parent, and those 2 nodes, the left and right subtrees are called siblings. The same terminology we used in general trees. A child has only one parent, a parent has at most 2 children, that is where the difference comes. So, again just to look at children, node with no children leaves left and right subtree of node I call the children, and the left and right subtree themselves are called siblings, and I is the parent, and a node can have only one parent child, and a parent can have only at most 2 children. So, that is the binary tree abstract data structure definition of the binary tree. A binary tree ADT is an ordered tree with the following properties. Each node can have at most 2 subtrees, we are just defining it again. Each subtree is identified as being the left subtree or the right subtree. So, here we are going to define a binary tree ADT in a little more formally. So, the binary tree ADT is an ordered tree with the following properties. Each node can have at most of 2 subtrees, and each subtree will be identified specifically as a right subtree and a left subtree and a right subtree, and each of the subtrees or the original binary tree itself may be empty. Now, what does this mean? The property 1 says that each node can have at most 2 children, and the order between the children of a node is specified by labeling the children as a left child and a right child. So, this is the basics, we are just repeating it and emphasizing that. Now, there are many ways in which examples of binary trees. Here we are talking about a binary tree example, which is an expression tree. Now, we have seen these expressions a lot when we were talking about stacks. Now, here you have an expression a plus b minus c into d, and we want to do b minus c first, multiply it by d, and then add it to a. This is the order in which we want the expressions to happen. It has been bracketed a little extra. So, this is a central data structure in any compiler design. So, interior nodes will always contain operators, and the leaf nodes will contain the operands. So, this is the way the expression tree will be defined. This is an example of a binary tree. So, it is the expression tree is evaluated by applying the operator at the root with the values obtained by recursively evaluating the left and right subtrees. Now, let us look at this. Now, you have b and c. So, b, why do we see, remember, if I want to evaluate the star, its children should have been evaluated. If I want to evaluate plus, its children should have been evaluated. So, obviously, the order in this expression tree b and c, b minus c will first be evaluated, the value put at the root, we do not have to say about value being put at the root, you will get a value, that value and d are multiplied, and that value, the value you get as a result of that is added to a. So, this is the way the evaluation happens. Now, another example of binary tree is Huffman coding. You will see as we go along, binary tree examples are very much realistic and used, I mean real time and used quite specifically. Expression tree was used for in compilers for evaluation of expressions and so on, for representation. Huffman coding is it is used in a simple but effective data compression algorithm, very important in computing. In this tree, each symbol is stored in a leaf node. So, here what is the their operands were stored, here we are storing the symbols that we want to represent. Now, to generate the code of a symbol, you will traverse the tree from the root and reach that contains a symbol such that each left link corresponds to 0 and right link corresponds to 1. So, the code of A is 0, the code of B is 100, the code of C is 101, and the code of D is 11. Okay. So, this is the encoding of the symbols A, B, C, D. Now, this is generated automatically. Okay. Now, if you want to have an effective Huffman code, you have to see that the symbols that are less frequently occupied are at the lowest depth, and the ones that are more frequently occupied, the symbols that are more frequently occupied occupy the top levels. Then you will get the code will be more effective, because you see A, if it is occupied, I mean if it is occurring very frequently, will have only one digit 0 as its code, while B and C will have a 3 digit code. So, this is the Huffman coding. So, you will see that the tree representation is what we are concentrating here, not the Huffman coding. So, tree representation is a typical way of representing the Huffman's code. So, the next so those are the two examples we saw. Now, we will define, there are certain definitions that are very specific to binary trees. This is a full binary tree. What does it mean? What do you mean by a full binary tree? a full binary tree, all nodes that are at the level less than h has 2 children. There is no question of one child in a full binary tree. All nodes from the top to except the leaves, everyone have more than have 2 children. There is no question of 0 children at any level other than the leaf. There is no question of one child at any level other than the leaf. So, where h is the height of the tree. So, less than all levels we will have that. Each node will have left and right subtree. So, at the level 1, okay, the number of nodes at level 1 and the previous levels we are looking at, number of nodes at this level is 1, okay, at level 1 is 1 because it is 2 power 0, at 2 it is 2, at 3 it is 4 to the power of 3 minus 1. So, that is 2 to the power of 2, 2 to the power of 3 minus, why 3? Because the level is 3. So, 3 minus 1, so that is 2 to the power of 2. At level 4 it is 2 to the power of 4 minus 1, 2 to the power of 3, that is 8. So, number of nodes at level so you will have 1 and then 3, 7 and 15, those are the number of nodes you will have at each and every level. So, you have 1 at the first level, 2 you will have 2 plus 1 3, 4 you will have that is 4 plus 3 7, and at the total number of nodes we have are 7 plus 8, previous plus this, that is 15. So, a node with level 4 or height of 4 will have 15 nodes. There is no question of any other. So, the number of nodes is fixed. So, suppose you have only 3, the number of nodes will be 1, 2, 3, 4, 5, 6, 7. If it is only 2, it will be 3. If it is 3, it will be 7. If it is 4, it will be 15. So, this is a full binary tree. So, you have something called a complete and balanced binary trees. A complete binary definition is a binary tree full down to level h minus 1, level h is filled from left to right, then it is called a complete binary tree. It is not necessarily full. Okay. For example, this is a complete binary tree because up to that level it is filled correctly. So, it was always filled from left to right. As you see, the last level is not filled completely, but it is filled from left to right. Balanced binary tree is another definition that we have, or another type of binary tree. The height of any node's right subtree differs from the left subtree by at most 1. The difference between the height of the left subtree and the right subtree can at most be 1. Okay. A complete binary tree is balanced, because if you look here, if you look at this node, one node, you will have the difference between the heights is only 1 of the left and right subtrees. Okay. So, that is the definition of a balanced binary tree, and a complete binary tree will always be balanced. Now, let us look at the operations on binary trees. So, the binary tree ADT has the following types of operations. Again, we are going to talk about generic accessor operations. Positions are used to abstract nodes. So, root returns a position of the tree's node, an error occurs if the tree is empty. Parent P returns the position of the parent of P, an error will occur if P is the root. Okay, I think this is fairly understandable. Children of P returns an iteratable collection containing the children of node P and stores the left child of P before the right child of P. Now, this is assuming it is an array, we will come into this later. So, but anyway, it returns 2 children. Okay. Then you have specific accessor operations. This is specific to binary tree ADT. So, position left of P. So, returns the left child of P, an error condition if the P has no left child. Right of P returns the right child of P and gives an error if there is no right child. Boolean has left, tests whether P has a left child, and has right again is a Boolean function, just tests whether P has a right child. So, these are accessor operation, gives the left child of a node, right child of a node, checks whether root node has a left child, has a right child. We do not have to use all the operations, it is just that we are giving a generic set of operations. Then you have generic operations, size returns the number of nodes in the tree, is empty, tests whether the tree has any nodes or not. Iterator returns an iterator of all the elements stored in all the nodes. This is specific to tree applications. So, it just takes and gives you all the elements of all the nodes. Position returns an iterative collections of all the nodes in the tree. Okay. There it returns the elements, that means actually what is the data in those nodes, while positions will give you all the addresses of the nodes in whatever way the implementation is happening. We have not specified the implementation as yet. Then you have query operations, normally is internal, test whether this is similar to our general trees. Is it an internal node P, test whether it is an internal node, it tests whether it is a leaf or an external node, test whether a particular P is a root node. Update method, again the tree ADT supports the following: replace P with E and return the elements stored at P. So, now let us look at some of the representations of binary trees. So, first we look at array representation of a binary tree ADT. The nodes are stored in an array based on the way of level numbering. I will come to that. Level numbering the nodes of T, some numbers are skipped through numbering process. So, here we have these are the nodes. This is simple and efficient implementation. Root, parent, left, right, has left, is internal, is external, is root, is just an arithmetic operation. Okay. So, that way it is a very simple and efficient operation. So, now, so this is the node 1. So, plus it is an evaluation, I mean it is an expression tree. So, plus occupies the first position, then star occupies the second position, it is level by level, and then 3 occupies the third position, then 4, 5, 6, 7, then this is left because 8 and 9 should have been 2's children of the 2 nodes children, it does not have any children. So, you have to leave a gap, and then you have A occupying 10 and then 11, and that is all. So, this is the array. Now, you would have seen, now the operation is very simple. So, suppose you want to find the root, root is 1. If you want to find the parent of, we will come to this in detail later, but what you will see is this is an array representation. The array will be completely occupied if it is a full binary tree. If it is a complete binary tree also, it is okay, because they will have less number of positions that are empty, but if it is a very skewed tree, this is a not a very good implementation. So, for this array implementation, for each node V of t, let P of B be the integer defined as, if a node V is the root, then we say P of V is equal to 1, that is the position. If node of V is the left child of node U, then P of V is equal to 2 into P of V. So, if you look in the previous one, you will see that if the node is P is V is occupying or U, V is the left child of U. So, U is occupying 2, the left child of U will occupy 4. If U is occupying 3, the left child of U will occupy 6, and the right child will occupy 1 position after that. So, if U is 2, the left child right child of U will occupy 5, if U is 3, right child will occupy 7. So, that is 2 into 3 plus 1. So, simple and efficient implementation. As we already saw, root you can find out, root is nothing but suppose I want to find the root of 6, I just have to divide it by 2. If I want to find the root of 7 also, I divide it by 2 and take the divide this thing only. So, 7 by 2 3, and if I want to find the parent, that is if I want to left and right, it is just 2 into 3 and 2 into 3 plus 1. If I has left, you have to see whether that position, you calculate the position, find whether it is occupied. Similarly, for this is internal, I have to find again the position and see whether it is occupied. I mean it is occupied, if the child is occupied, then it is internal, if the child is not occupied, it is external node. Root is, it should not, root should be 1 only. So, this is all simple arithmetic operation, everything to do with that that you are storing the children left and right at 2 into, suppose the node is 2 to the power of I and 2 to the power of I plus 2 into I and 2 into I plus 1, not the power, 2 into I and 2 into I plus 1. So, the space complexity implemented by means of an extendable array. N is the number of nodes in T, P of U is be the max, the value of P of V over all nodes of T. Size of the array will be P of M plus 1, and since 0 to S has no nodes stored in it. In worst case, it will be to the power of 2 power n. So, time complexity size is empty 0 1, iterator and position 0 n, because you have to go through the complete array, replace 0 1, all other operations root, parent, children, left, right, has right, internal, is external, is root, everything is 1. Only thing, the array size is very large. Now, we go to the next and very common representation of binary tree, and that is the linked representation of the binary tree. So, a node is represented by an object storing, it has an element, and it can have a parent node. There are other representation also. This particular representation, it is a linked representation, but also gives you the parent node and the left child and the right child. There is another representation where you do not have the parent node link, which depends on what type of operations you do and the representation you want to have. So, and the node objects implement the position ADT. We assume that there is a position ADT available to you. So, this is the thing. So, if you look at the node B, again we are using the small tree there. So, B does not have any parent, so that is null, and the left child is pointing to A, the right child is pointing to B, and the value B is there. And if you take A and D, A is pointing to B as its parent, it has no left child, it has no right child. D is pointing to B as its parent, it has left child C and right child E, and C is pointing to D as its parent, D is also pointing to D as its parent, both of them do not have any children left and right. So, this is a linked one of the linked representation of a binary tree. Now, here the space complexity of the order of n operations, some of the operations like iteration and position of order n, and most of the other operations takes 0.1. So, now let us look at binary tree traversals. We just looked at traversals from the general tree, but it is much more important to look at it from the binary tree angle. So, to process a node means to perform some simple operation like printing the contents of the node or updating the contents of the node, that is the meaning of processing. Traversal means to traverse a finite collection of objects, process each node, process each object in the collection exactly once, that is the traversal. So, pre-order traversals, each node is processed before any node is in either of its subtrees for binary tree. In order, each node is processed after all the nodes in the left subtree are processed and before the right subtree is processed. Please note the definition is different because we are talking about left and right subtrees. Post order, each node is processed after all the nodes of all these children subtrees are processed. So, this is pre-order, in order, post order. I will repeat, pre-order, each node is first processed, then its left, then its right. In order, left subtree we will say, left subtree, it is a recursive definition, left subtree, root, right subtree. Post order, left subtree, right subtree, root. Okay. So, that is the binary tree traversal. You also have another traversal called level order traversal. Each node at level I is processed before the next level is taken up. So, it does not follow any of the left subtree issues. So, we will take each node. I have got a small simulation of this. So, pre-order, visit the node, visit the root, visit the left subtree, visit the right subtree. So, algorithm is again a recursive definition, process node n, then that is whatever the node is, okay. Process node n, traverse pre-order the left child, traverse pre-order the right child. So, how do we do this? Now, I have the node A. Now, I have to process according to this I have to visit A first. So, A is visited, then I have to visit its left subtree. So, the whole subtree is visited. Now, I call this algorithm again, okay. Please note this whole subtree is now called as traverse pre-order the left subtree. So, again this is the left subtree is calling the recursive algorithm. So, I visit the root. Now, after I visit the root I have to traverse, I have to process this left subtree. So, again there I visit the node. So, that is it. Now, this after I visit this I have to process the left subtree. So, I process the left subtree. Now, the left subtree does not have any children, either the left or the right. So, I have finished processing that call to left subtree. So, I go to the right subtree. So, I process that. Now, the right subtree when I am processing, visit the node, visit the left subtree, visit the right subtree. So, that finishes up to now actually I have finished processing B's left subtree. Okay. So, now I go to B's right subtree. So, now here again I visit the node, left subtree, right subtree. Up to this point, after this point I have finished processing A's left subtree. So, I have to process A's right subtree. So, I go here and then I process the root node, I process the left subtree has only a G. So, I finish that. So, now I finish processing D's left subtree. Now, I have to process D's right subtree. Now, that right subtree I visit the node, I visit the left subtree. Now, this left subtree I visit the node, visit the right subtree, visit the left subtree. So, I have finished pre-order traversal of the particular tree. and you will see that this is the order in which the nodes have been processed. Okay. And we will see later on in expression tree how this is how it gives you some infix postfix expression that we saw in stacks. So, now let us go to the next. So, we are going to do the in-order traversals. Now, when we are doing the in-order traversal of a binary tree, we have to visit the left subtree first, then process the node and then visit the right subtree. So, the algorithm is that if n is an internal node, then traverse in order the left subtree, process the node n, and then if it is n is an internal subnode, then traverse the right subtree and so on. So, here what I have to do, I should not process A first, I have to process A's left subtree. So, A's left subtree is rooted at B, I have to process B's left subtree. B's subtree is rooted at I have to process I's the left subtree of I. So, I have K. Now, I have to process the node. So, I process that. Then I have to process the left subtree, I am sorry, the right subtree. Right subtree is rooted at L, and in the when I do that, I have to process its left subtree first, that is I, then the root, then the right subtree. Now, I finish processing the left subtree of B. So, I have to process B. So, I do that. Then I have to process the right subtree, again I have to process the left subtree of H, which is M, then H, then the right subtree. Now, I finish processing the left subtree of A. So, I have to process A, then I have to process the right subtree which is rooted at D, for which I have to process the G. So, I do that, then I have to process D, then I go to the I have to process the right subtree of D, which is F, for which I have to process the left subtree of F first, which is rooted at O, for which I have to process the its left subtree, which is R. So, I process R, process the root, process the left subtree. Now, I finish the left subtree of F. So, I process the root and I finished. Now, this is in-order traversal. Now, same thing we can talk about post-order traversal. Post-order, I visit both the children left, right, and then only process the root. So, for A I have to process B, for B I have to process I first, then H, then come to B. So, I process K, then I have to process this L, but for that I have to process T and S, process L. Now, I finish the left and right subtree of I. So, I process I. Then I go to it should not process B, I should process the right subtree. So, I finish M, I finish N, I process this, then I process B. So, I finish the left subtree. Now, I have to do the right subtree. So, I process the left root, then I have to process the right. So, I do this, then 13, I finish all the subtrees of F. So, I finish F, I finish all the subtrees of D now. So, I process D. Now, I finish all the subtrees of A. So, I process it. This is the post order traversal. Now, I have an expression tree. I am going to do the same expression tree, the same traversal, just to show you how it gives different expressions. So, first we will see the pre-order. So, remember what is pre-order? Pre-order is root left, okay, then that is left, then so I have this, then I do the root, then A 1, and then I do again this, I finish this. So, I do the right, okay, and so on. Okay. So, this gives me the pre-order expression. Now, I have to do the same thing for in-order. So, in-order is left expression right. Now, right left expression and then the left expression and then the right. So, now I finish this subtree. Now, I have to do the 1 and then I have to do the root node. So, I finish that. Now, in the right subtree I have to do the 3, okay, and then the operation and then this. So, that B. So, this gives you the in-order expression. Now, the same tree, remember we have used the same tree, we are just traversing in different orders. So, now what happens? I have left, then I have to do the right. For the right I have to do the left, right, then root. Now, I finish both. Now, I have to do the processing of the root of that multiplication. Now, I have to do the left right similarly. So, 3 B star and then I finish both the left and right subtree. So, I do this. So, this gives me the post order expression. So, same thing I can do for level order also. Level order is just you just keep on doing till you finish all the children level by level. So, this is a simple level, visit the root, visit the left subtree, visit the right subtree level by level. So, that is the so, the binary tree ADT, I have an empty tree, the precondition is no precondition, post condition is returns true if the tree is empty, false otherwise. Traversal, I can give the order and the ordinal. So, precondition binary tree should not be empty, post condition is traverses the binary tree according to the value of the ORD. ORD is the order you want, it could be pre-order, it could be in order, it could be post order, it could be level by level also. So, order pre-order, it traverses the tree using pre-order, in order traverses the tree using in order, post order it traverses the tree using post order, or level order it traverses the tree in level order. So, that can be an ADT that you define, where traversal is very important. This is the Euler tree traversals of a binary tree. Here we visit the node more than once. This is a generic traversals of a binary tree and includes as special cases pre-order, in-order and post-order. You walk around the tree and visit each node 3 times, on the left pre-order, from below post in-order, and from the right on the right post-order. So, unify all 3 traversals by reducing the requirement of each tree to be visited once. So, this is applications for calculating the number of disciplines of a node and print a fully parenthesized arithmetic expression. You normally use your Euler tree traversals. The specific what is the specializations of special cases of Euler tree are the other 3 traversals we saw. So, what is the summary of what we saw in this node? We compared general trees with binary trees, we discussed binary trees with some examples, and then we described operations on binary trees, and we discussed the representations of binary trees, both array and linked list, and we explained the various binary tree traversals that we have. So, this is what we explain in this particular module. We will be going into more details and implementations as we go along, but traversals is what we concentrated on with expression trees as well as normal binary trees. Thank you.